Again, we got that YouTube channel of physics. That's going to hopefully be kind of a constant feature. So that just takes you to the channel. You can find the day that you missed. It's usually going to be this class because you're my first class. Usually things go okay in here, and then that screws me up for the rest of the day. I don't operate as cleanly in the other periods. But I will, as a trade-off, I have to swear less in here and tell fewer inappropriate jokes. And I can't bully you as much as I would like to, but hey, can't have it all. We have a final tomorrow over CVPM and CAPM, so please bring a pen or pencil. Probably a pencil would be better, and a calculator, because there will be some quantitative analysis of motion on there. But it is strictly CVPM and CAPM. I got a couple links for you for some practice with graph shapes and interpretation. You can also go back into Canvas and just look at worksheets we did in CVPM and CAPM and get some practice with that if you need it, okay? It's 20 questions. It's multiple choice. 40 points, though, in the grade book for that. And what else is happening? It's about the size of it. So, again, Pear Deck back channel is open. FQIKA. It's a Q. Does that not look like a Q?
I thought it was an N. I couldn't really see.
That's quite clearly a Q.
I have the glare right there.
Okay, fair enough. That goes away. Oh, here we go. This is what I was looking for. So OneNote. So we talked yesterday. Where'd that go? Oh, we moved it. Okay. So I moved this down here to the next page. So this is part 2. So it's an 80 kilogram box. It starts from rest, travels to the bottom in 2 meters, or that's how far it goes. But the motion is opposed by 150 Newton frictional force. So you know what the frictional force was in the initial CVPM case. Now if we have less friction, if it's only 150 Newtons, what's going to happen? So that's what we're going to check out here. Let's hear from my dear friends from Group 1. Hey, Group 1. Come on down. And again, if you're up here or seated near here, you're being recorded too. So try to cut down on the foul language, okay, Andre, and the inappropriate jokes, Pedro, and should be good to go then. So.
Jerry.
Mm-hmm. Oh, Jared was on fire yesterday. I had to listen to that back. All right, Group 1. Part A wants to know what models apply and why. Can you hit us up with that, please?
All right. So, constant velocity particle model. I did not fix this. I did not. Don't listen to that. Opposite of that.
Go ahead and
constant
amend that.
Acceleration particle model. Because there is constant acceleration, so is unbalanced particle model. Unbalanced source particle model.
What tells you that that's the case?
Because when you take a look at the balanced forces diagram, they do not balance. Because that's why it's an unbalanced force diagram instead. Because you've got some force unbalanced right there that's going against the normal friction force of 150 newtons.
I don't know.
What is the abbreviation for
UBFDM.
UBF?
All right, UBFDM and CAPM. You established that based on how the diagram shook out, then once you put the forces in there?
Yes.
What about the prompt also cues us that this might...
Oh, it starts from rest as well, and it manages to get to the end.
There you go. So that's another thing to look for. There's a mention that it starts from rest, and so if it gets somewhere, had to accelerate at some point. All right, cool. Go ahead and flip another board to talk to us about one of the graphs and/or diagrams. And go ahead and tell us about one of your graphs and/or diagrams and what quantities you solved for out of that. All right, so what's something you graphed and/or diagrammed?
Okay, so I basically just took the old graph from when all of the forces were balanced, and I just chopped off a little of this, or chopped off a little of the friction force. And just using that equation, Newton's second law, you can find the acceleration constant of 1.54 meters per second squared.
Can you walk us through the using that thing? So we had 150 newtons of friction. What'd you do with that?
So you just like chopped off 123 newtons of force,
Because originally we had,
273.
there we go.
And then, so you can just set 123 newtons equal to 80 kilograms times the acceleration constant. And then you can just solve for A, which is just 1.54 newtons per kilogram, and the equivalent for newtons per kilogram is meters per second squared.
Okay. And then can you be a hero? I see that there's tips on some of those arrows. Make sure we got tips on arrows in that thing. Okay. So if you look carefully at that, you can kind of see how it starts from the smoosh poosh arrow, then there's the gravity arrow drawn on the end of that, and then the friction arrow is drawn on the end of that. And maybe in a different color, can you add in a FU arrow to that HPD? Which direction is that FU pointing? All right. Can you see that, friends? Any questions or concerns on that FU arrow? I need to have the pear deck open back here. This is why we want to be cautious about thinking that knowing the name of something means that you know anything about it. Hey, I got pear deck open too. So joinpd.com Kika and ask a question, and I'll display them back here. How about that? So go ahead and type. Or is it not a question? Dang it! All right, give me a moment. Come on, pear deck. All right, all that. And that. New question. Ooh, they sat down. I don't know why they did that. All right, so what questions might you have for them as you're trying to help them out with that diagram? This is perfect because this is exactly what I need you to be thinking about with this. What you think about it? Later. This is so much faster than raising hands. You're a genius, Mr. Frank. Thanks, kids. All right, and okay. So let's, yeah, there's a couple of questions. Thanks, Charlie. So we only need to be looking at the CTD, or not CTD, what do you call it in here? HPD, okay? And so the questions your friends have for you here, that's not what I meant to hit. Let's go. Ooh, show responses. All right. So why is the FU arrow facing the way it is? That's their question for you.
What gives you change? What gives you reduce the friction? So then, like, that's the Good job. Yeah, but you reduce friction and unbalance.
So when we're drawing this arrow that represents the unbalanced force, did you draw an arrow that represents the unbalanced force, or what it would take to balance this out?
What it would take to balance it out.
So can we go up there and change that then, so it shows us how unbalanced it is? And so that's the other thing to think about with this, as it's sliding down the incline, which direction is the acceleration? This is something we talked about the other day with the elevator activity. You want to add in an arrow that shows you the direction of the acceleration on your diagram, or not on your next to your diagram, and then you can reference your unbalanced force. Okay, the FU should be pointing the same way as the acceleration. So now we see an FU pointing down the ramp, and that's going to help us understand why this thing is accelerating in that direction. Okay, it's accelerating in the direction down the ramp. It's getting faster that way because its acceleration and motion are pointing the same way. All right, thanks, Route 2. Go ahead and flip another board to talk to us about another diagram they have up there. And make sure you've got that corrected on your page. Again, my recommendation, if you're struggling with the direction of the FU, is to think about the direction of the acceleration. All right, Group 8. Talk to us about something other than the HPD. Jonathan. You cool with Simon's value for the acceleration? Yeah, looks like it. Okay. So we've got that acceleration. Where can we go from there then?
One of the things that we did was a velocity versus time graph. So we know that the distance traveled was 2 meters, and the slope of the velocity versus time graph is 1.5. Is that what we have? Yeah. So you can set that up to find the area of the triangle is equal to 1.55x squared, with x being the amount of time that it takes to get down the ramp. And then you can use that to find how long it takes to get down the ramp, and then plug it back in to find the final velocity.
What'd you get for any of that stuff?
Time we got 1.6 seconds, and final velocity we got 2.48 meters per second.
All right. Any questions or concerns on that? Go ahead and throw them in the pair net quick. And this is the part of this problem that's germane to what you're going to have to do tomorrow on the final, right? You've got the change in position. You have to know how that change in position shows up on a velocity versus time graph. One of the more pain in the hind end types of things to have to do is, given the acceleration and the slope, to figure anything out. Can you kind of, yeah, exactly. So mathematically, what did you do with that 2 meters to then figure out time and acceleration? Can you just kind of walk us through where that's at on there? It's on there.
Yeah, it's in the box on the top right. So we ran out of space at the bottom. It's a little box with the dashes in it.
Oh, okay. Can you talk us through what's happening in that little box?
Okay, so you have the area of the triangle is 2 meters, because that's the distance that it traveled. And then for the area of the triangle, you do 1/2 base times height, and we have the base per time being x, and then the height being 1.55x,
And why is that?
because the slope is 1.55.
So if you did the change in y, 1.5x, divided by the change in x, you get left with 1.55, which is the slope. Okay.
So then you get 2.58 equals x squared, and then you just take the square root, but time has to be positive, so you get time is 1.6 seconds. And then you can multiply, so you find that time is 1.6 seconds, and then you can also use 1.6 for x with the height, which is 1.55x, then you just plug it in and get 2 meters per second.
That's how that all shakes out. So those are the types of things that you're going to be asked to do on the final tomorrow. Okay. Can you go ahead and flip another board, see if they can talk about something besides the velocity time graph or the HVD? All right, 128. Hop on up there and chat with us, if you would, please. And so the other thing I'm looking for here, you got a velocity time graph, you've got a HVD. Talk to us about the shape of your position versus time graph. Why are you thinking that?
Our position time graph?
Yeah.
Well, we only had it going that way because we weren't sure if this was going in a positive direction or negative direction where the sensor would be and how it would show up on the graph.
So where is the sensor for yours?
For ours, it's going towards the sensor, so it's at the bottom of the ramp.
So why should that shape make sense to us then?
That shape should make sense because it's speeding up in a negative direction when it's going down the hill faster.
So it starts out very flat, very horizontal, and gets steeper over time in the position time graph. Okay, cool. All right. Any other questions or concerns on any of this? All right. So I think we can call that bueno. And then what's going to happen in this last part, and this is again, when I talk about this like a progression, you're going to have situations where something's on a frictionless incline. I think it's helpful for you to initially pretend that it is CVPM and then take out the friction, because that's going to allow you to know if now there's no friction. Can anybody tell me without touching a calculator, if we get rid of the friction arrow there, how big is the FU? If we get rid of the friction, now the FU is, there you go. Okay, so grab your board and have at that, and see where you land. Let's see how quickly you can power through that. I'm guessing fairly quick.
Appreciate the compliment.
What?
I'll grab a sock.
Or maybe you won't actually.
Yeah, I don't know.
Wait, no.
Software
We can keep this.
And then we
Where
get
is
to
it? How
how
much
much
we?
Yeah. And take out.
Constant accelerator. Yeah, but that's fine.
This
We're skipping
is
gravity.
except for this. This can. This part. There isn't any even. That is the exact same.
By the way, actually, they're like
I'll work on the.
Again, you should be like filling this stuff in on your sheet for notes as you go, right? Like, that'd be a smart thing to do, because the UBFPM test might not be until after, hopefully it's before Thanksgiving break, but it might not be until after, so it might be a couple weeks, you have to think back before people.
This is fine.
Second try gets strange.
Why are you leaving?
okay. So nowhere. I'm just like getting in a good time. I don't know. Okay.
Still edging. I'll draw the F because I'll. That's it was like red and black because you drew the black line was red. So equals.
Wait, what's 80? The weight?
80A.
Yeah. Here, right? I'll take enough help. Wait, no. The acceleration should be. The acceleration is that doesn't mean end velocity. Yeah. Because this equation. Oh yeah, 1/2 at squared. Dang it, Glenn. We're dividing. 1.09. Yeah, 1.09 seconds. Actually, 0. No,
Divided by 2.
and then
Oh, yeah.
that times 3.4.
Okay, so 3.
Area of this is
No, because I was going down. Okay, I have to keep my bad.
Anything else yet?
Danny, why did you
We all agree on all this.
Good.
Good.
Lane 5.
Ethan, I've been waiting for the last 5 minutes. It'll be a little bit.
Okay, I think we're good.
Yeah.
I got you. Then I'll.
You're fast. I don't like that.
This is going to be really funny.
What are you talking about? No, why would I joke about
I just realized that's something that was cool.
Oh, you got ice cream? Hello, Secretary again. Thank you, Secretary again.
What was the velocity on the last one? 2 point. The previous one with 150 newtons was like 2.6 ish, something like that. All right, what's up, sir?
I don't have to create this.
Oh, you get a light stand on this stuff. Whose is this? Oh, everybody had to do their own, and everybody had to do a different version of it. So if you want to do that, since this one is solved with the equation for challenge one, you can solve it with like a motion map. Since this is solved with a position versus time graph, you can solve it with a velocity time graph. Since this is solved with a motion map, you can solve it with an equation. So everybody in the group had to solve it a different way. Yeah.
So it wasn't like a group.
No, it was like in the, yeah, you can go back and look at the instructions.
Right?
All right, boards are pretty much up front. So let's go ahead and hear from Tao. Come on down, Tao, and talk to us about what you got going on in
Okay, this is a mess.
Don't put up these everybody down. All right, Tao. There's no friction.
Yeah.
What happens?
So FU looks like that. We've already discussed that. But
Hey, hold on one sec. Hey, audience, let's try to play along here and see if you can hear what they're talking about. There's no friction, so run us through what doesn't change and what does change. Okay.
so FU changes.
Mass doesn't change.
Mass doesn't change. So then, since FU equals M times A has to
so
change.
mass doesn't change.
Mhm.
So what else doesn't change in that diagram then?
FSP.
Yeah, this has 750.
FG. Okay.
Yeah.
What else did you not change in that diagram?
FSP,
Yeah.
Okay. Why does it not change?
because it's still
This
pushing down as much.
same angle.
Yeah.
Same angle as the incline. Okay. All right. So then what does change?
Yeah,
Acceleration,
Okay. Por qué?
because FU changes and mass doesn't. So then.
And what is the FU now?
270.
Okay. So 270, and then the mass is 80. What'd you get for the acceleration?
Not nice numbers, but what was it?
3.38.
3.38. Okay, cool. Go ahead and flip another board to talk to us about something they did. All right. 9.81 newtons per kilogram. So the HPD change.
There we go.
You agreeing-ish with them on their value for the acceleration?
Yeah. Yes.
Okay. So, friends, this is kind of the process of this model. Use the diagram to establish what the FU is and which direction it's pointing. And then, now we're going to use the equation to figure out the acceleration. And what did you end up doing with that acceleration?
So with the acceleration, you figure out the slope on the v versus t graph, and then you know the position. The difference in position will be 2 meters. So you figure out the area of this thing, and that has to be 2. So you can figure out the time. And so 2 equals 2.42 times t times t, and then you solve for t, and it's like 0.76.
Okay, so they've got a time of 0.76. They just walk you through how they got that. You got any questions for them? You might think about how that compares to the value you got, and that might help you find a question to ask. Also, this is kind of where I need you to engage with the presenting, so try to pick up on this stuff. All right, now we got some people asking questions. Give me a second, my little finish it on. All right, so it looks like the concerns are with the time. How did you solve for time? How do you find the area of a triangle? How did you find the
Oh yeah, the area of a triangle is 1/2 base times min.
All right. Well, game. So what's that going to do to that number?
So it changes to 1.08.
1.08. All right. Oh, So now that time is 1.08. Did that allow you to find anything else here then?
We could find the velocity when it reaches the bottom.
Okay, and how would you find that?
You multiply 1.08 times 2.42.
Okay, what's that gonna roughly equal?
About
3.5.
3.5.
Okay, go ahead and put that on your velocity time graph if you would, please. Okay, so about 3.5 meters per second. Any further questions for this group? I don't think so. All right, good. Looks good then. All right, go ahead and flip another board then to see who's going to tell us about something else. Group 1. All right, so we talked about the HBD, we talked about the velocity time graph. Can you talk about one of your other representations there?
What's needed?
We had a velocity versus time graph and an acceleration versus time graph. For the acceleration, we could solve for change in velocity because we had 3.452 for the acceleration, and then our time was 1.08, and then you just multiply those by each other with the area.
Cool. And that's another important thing to think about for the final tomorrow. Could one of you bother throwing that on that graph just so we can see what you're talking about? But that's what I was hoping for. Using the acceleration versus time graph to establish the change in velocity. So again, Emma, for the slow kids, aka me, you knew what parts of that rectangle?
Like height, like are you? We need the acceleration and the time.
Knew the acceleration at the time. So they knew the height because that's the acceleration on that rectangle, and they knew the base because that's the time on that rectangle. Solve for the area, and that gives you what again?
3.8 meters per second.
3.8 meters per second. That's an area on that graph, and as the lady mentioned, that's the what?
Change in velocity.
So do you want to fix that?
Where? We put per second.
Oh.
Point oh. All right, there we go. So change of velocity, 3.8 meters per second. Well played. You guys are doing great with the game today. All right. And so then all that leaves us with where are we to find the worksheet? There we go. Are these analysis questions? And so, let's see. Ooh. Yeah, grab your board and I want you to ponder these things together, okay? So take a look at these questions. You can just answer them right on your sheet. And then I may random pick some folks to have to talk about it. Here it is, like a random pick on you.
Worth it. I just need more questions to answer these, right?
Yeah.
Or do we have?
Oh wow, I participated in the October Pear Deck Challenge. I did not know that. We didn't win.
What's the October Pear Deck Challenge?
I don't know, we didn't win, so.
Okay, well, someone.
They already gave it to me for free, so I don't know what I would win if I.
Pear Decks every day.
Hey,
More Pear Decks.
it's almost like we already do that.
I'm surprised. For how often you
Hey, the person that I stole this from calls the smoosh boosh the support force. So anywhere it's talking about a support force, that means smoosh boosh. On the analysis question.
Receiving.
Okay,
I prefer switch myself.
greater than less, because we found that.
Okay, we're going to agree.
Andre already did.
Oh, your answer.
Yeah.
Okay, good.
That is beautiful writing. Somebody else will do this. Because we did the math. Oh, because it wasn't going straight.
Because friction had a little bit of vertical force, but when you took
All of
friction
four
away.
on the whiteboard. I mean, kind of, right? Hey, so it's asking you to like make comparisons to what you had. Yeah, I guess. Yeah, go ahead and throw it on the whiteboard. That'd be smart. Let's do that way.
We need to explain.
For tomorrow, go back into Canva and like look to see if you're.
You could just say they found a.
I don't know.
It's like
friction has over 50s last time.
And then like the stuff that we're doing right now.
Okay, you probably okay. Yeah, if you're 7 seconds. So, I mean,
So are we saying that we would have a small amount of while?
Yes.
it says to have a unit 7 seconds or true electrification.
So there's the
So draw like
either the friction or
which video that we
Friction
had.
would be passive or friction.
so when
Bigger.
No, it's acceleration. What's the constant?
Okay, so divide 3 by 3.42.
That's FG, that's FSP, that's FG. That FG.
Or it could be FS.
I do know the.
There's a problem to me how which is well, friction.
Oh yeah, that's true.
So how do you want us to put these up there?
Once you got it, yeah. Do you have your compare? Like, can you? So that part it talks about making comparative diagrams. Can you actually like show on there what the diagram would look like, what you had, and then when you change it? Yeah. Does it say vectors?
Yeah.
I stole this from somebody that speaks German. Jeepers.
No, that's
Wait, is the big one or the little one? Is this? Oh, this is the first one. So we're gonna go nice and low. This, yeah.
Is that
So it's gonna need to be lower. It's going like this way, yeah.
Whoa.
You donkeys.
Riley just dropped all my stuff. That's fine. There we go. Note to self, never double Riley up right now.
alright, next up you got.
So let's say like forward and
Front side out.
Yeah, for sure.
Hey, Hardy, was the force from the Earth's gravity?
Yeah.
Not mine.
then
is FP.
So that's like. Okay. So that's the change.
No. Wait, do we care about FU or SP? Yeah, SP. We care about FSP.
Yeah.
Was the support force?
Yeah.
How would our answer about FSP from this video? Beautiful. One determining unbalanced force in problem one, but yeah.
Hey, Sophia Chen kind of blew my mind the other day. I didn't know this was a thing. Maybe you already did or you didn't. But like,
That's my scientific calculation.
yeah. Spoilers, Jared. So like Desmos, like I'm used to going to Desmos and I like the graph, right? But yeah, if you scroll down here, you got a scientific calculator. What's the geometry tool do?
You can make circles and lines and draw stuff.
Oh.
It's
So when you're bored with 2048 in Tetris, you can go make circles and squares and lines and stuff. Ooh, but here's just a calculator. So if you just need a calculator, look at that. Yeah, you can do that too. But I mean, like, hey, that's kind of nice. Maybe, I don't know. Maybe you didn't know that. Maybe it's nice.
You can still use variables.
Oh, into that?
Yeah.
Like I can trick it into solving things for me?
No. Like you can have like x's
Okay.
say fu and be like, okay, if we put in this for x, then how does this get 0?
Okay.
But you can do that in
So it's basically the graph without the graph.
yeah.
Okay.
And you can only put one variable.
I mean, also you can just like.
Unbalanced force in the square. Wait. Problem one. Remember, problem one. Yeah. Problem one. Like there's a constant speed, so it's 0. The unbalanced force is 0.
Yes. It really just is.
Alright. And 3, the unbalanced force.
So again, you can throw your stuff for number 4 on the board. That part where it's asking for comparison of the diagrams, that's the part that I'm really keen on. So put a little thought into that. How would, and again, I've kind of said this a few times. Think about how it would look if it was BFPM, and that might help you kind of contemplate what's happening to the sides of the triangle.
It's 270, right? And it's 270. They're the same.
Okay, so if they're different, explain because the FU state detectors the force is the same with the entire like the velocity is on one of them.
Wait, yeah.
I'm going to give you a heads up too. The quiz will not take the full period tomorrow, so I'm going to have a sort of an in-class assignment, if you will, of sorts. I want to start getting you more practice with linearizing graphs because A, that's a skill that will show up on the exam, okay? And I hate that that's kind of like my rationale for why we're doing more of it. It also is a good data analysis skill, so that's kind of the more altruistic version of why we're doing it. But we ended up with a graph in the most recent lab that was not linear. And so I'm putting together an assignment where you're going to take that Desmos graph and then linearize it, okay? And I'm going to try to have us do that a few times each trimester so we're practiced at it. Because that is a test-taking skill.
Starts at -3. We're gonna have practice tomorrow.
Just 2 seconds.
Huh?
The answer for
Right.
this one just 2 seconds.
On the last thing,
2 seconds.
you push it up the ramp so it's negative. and that's going down the ramp is positive.
How do you know going up?
Yeah.
Because
we've been referring to going down the ramp as positive the entire time. So I'm just gonna, for consistency's sake,
Yes.
Okay. So then we want to know the area under here, right? Because that's how far up the ramp will go.
Yes.
Okay, so
There's some questions we have.
here, we're gonna call that big head.
Charlotte.
What you're gonna take?
So
it should be a 10. Yeah. Okay, so what was our acceleration? 3.3 something. Yeah, 3.38. Okay, so negative 3 meters per second.
Yeah, over
Is
time.
this, so then this is that divided by acceleration, right? This?
So then the acceleration.
Yeah, this is time. But so changing velocity equals time times acceleration. Yes.
Yeah.
So then, time equals change in velocity divided by acceleration. Yes. Yep. Okay. So time divided by acceleration is 1.5 divided by 2. And that's the area. Yep. Let's fill up the graphing calculator because the first thing this comes first. Okay. We graph what? Negative 3. Let's just say 9 divided by 2.
All right, hey, I was gonna say it's about that time. So go ahead and store your boards in the back behind Natalie. Again, make sure you show up tomorrow with a sharp mind and a sharp calculator and a sharp pencil.